Alright everyone, so this is the last example for this chapter. We have a light spring that has a force constant of 125 newtons per meter. It's being used to pull a 9.5 kilogram sled on a horizontal frictionless ice rink. We know that it's being pulled so that the sled has an acceleration of 2 meters per second squared. We want to know how much does the spring stretch if you pull the sled horizontally or if you pull it at an angle of 30 degrees above the horizontal. For part A, recognize that it's pretty much the same example as example 9. It's pretty much the same setup. You have the force of someone pulling on a spring, and you have an opposing force, but in this case the opposing force would be friction. With no friction, then the spring force is simply equal to the mass times the acceleration. For part B, it's just a little bit different, and the important thing to remember there is that the acceleration is 2 meters per second in the x direction, because you know intuitively that if you pull at a 30-degree angle, you would expect for it to accelerate at the same rate, that the spring would stretch more. But if you work this problem incorrectly, you'd find that the spring would stretch less. That should tell you you've done something wrong. So in this case, we have the spring force pulling to the right, and it's the only force, so we can set that equal to the mass times the acceleration. Based on Newton's second law, we know the spring force, k times delta x. So if we want to determine how much the spring will stretch, if we know it's accelerating at 2 meters per second squared, and we know the spring constant, then you find that the spring would stretch 0.152 meters, or 15.2 centimeters. When considering the same problem at an angle, remember that we would expect the spring to stretch more. And here the acceleration is still 2 meters per second squared in the positive x direction. This is because the additional force pulling it at an angle means that the upward force from the spring only works to counteract gravity. It doesn't work to accelerate the block forward. So we have to consider only the x component of the force when we determine how much the spring will stretch. We know the x component is equal to the mass times the acceleration, which means that the x component is equal to 19 newtons. To find the spring force, we simply use the fact that we know the x component of the force to find the magnitude of the force. So dividing by cosine of 30, we find that the force on the spring should be 21.94 newtons. And if we set this equal to the spring constant times the displacement, we determine that the spring will stretch by 0.176 or 17.6 centimeters. For the last part of this problem, you want to consider how friction would impact the spring. So for example, if the coefficient of friction between the sled and the ice were 0.2, how much would the spring stretch? Here again, you would expect that the spring would stretch more. And so we need only account for this additional force in Newton's second law. I would invite you to pause this video here and try to work this problem, and then watch the solution. So here again, now we have the spring, but we have the force of friction pulling backwards on it. We write the sum of the forces is equal to mass times acceleration, then the force of the spring minus the force of friction is equal to the mass times the acceleration. We know that the force of friction will be related to the normal force, or the weight of the object, and the contact between the surfaces. So we know everything in this equation except for how much the spring is stretched. And we find the spring would stretch 0.30 meters or 30 centimeters.